Hello, welcome to the lecture on network theory. In this lecture, we will be continuing with Thevenin's and Norton's theorem. We'll be doing problems for Thevenin and Norton's theorem. Okay. So in the last lecture, I mentioned that the type of problems that you might encounter in this Thevenin and Norton theorem portion can be divided into three categories. Problems with only independent sources, then with both dependent and independent sources, and then with only dependent sources. So let's solve a problem from category 1, which is only independent sources. Okay, let's do a question. Okay, 5 ampere, 10 volt, 3 ohm, 2 ohm, 1 ohm, and 2 ohm. Okay, the question is to find V using Thevenin and Norton theorem. Right, so what do we do? So first we define okay, let's just keep it aside. Okay, first we define the terminals we want to. So basically in this portion, questions can come in two ways. They can either ask you to find the Thevenin equivalent across a given terminal, or they can ask you to find the Thevenin, not the Thevenin, just a voltage or current across a given element. So that time what we do is we define A and B. We define the two terminals. We keep it aside. We keep this element aside, and we find the equivalent circuit across this terminal. We put the element back, and then we finally find the response. That is the way of doing it. Sometimes even for some complicated circuits, if they ask to find the response across an element, many times it is better to just simply use Thevenin or Norton equivalent circuits to simplify the circuit. Okay, I'm just removing this. So now we have defined our terminals. Okay, so first what do we have to do? We have to find the open circuit, right? VOC. So basically this voltage is the voltage across the 2 ohm terminal, 2 ohm resistance plus the 10 volt. Okay, this much, that is VOC. So this 5 ampere current will come here. We have 3 ohm here and 3 ohm here, so it will divide into 2.5 ampere and 2.5 ampere, right? So it will be so V open circuit VOC will be and this voltage polarity will be like this because of the current direction. It will be 10 minus 2.5 into 2, which will be 5 volt. Okay, which is equivalent to VTH. Then I am finding 3 ohm, 2 ohm, 1 ohm. I have a 10 volt here. Okay, I am finding the I short circuit. Okay, so if you see here, we have our 5 ampere coming here, we have our ISC coming here, so this will be I plus ISC, this current that will be coming through here. And here if you see, this 10 volt is acting, it is in parallel with this 2 ohm. So this, the voltage across this 2 ohm will be, what will it be? It will be 10 volt. That means the current flowing through here is 5 ampere. And since ISC is coming here, it will be 5 minus ISC. Okay. And here we have 5 plus ISC, which is coming here, and 5 is coming this way. So this will be ISC. So 5 is coming here, ISC is going this way, and this is 5 minus ISC. Again, ISC will join here. So 5 minus ISC plus ISC will be 5. So every currents check out. Now I am using one mesh. So let's take a mesh like, not a mesh, a loop. So I am using this loop to write the equation. So it will be minus 10 plus ISC into 3 minus 5 minus ISC into 1 equal to 0. Okay, from this we will get ISC as, if we rearrange, we will get ISC as 15 by 4 ampere. This is our I Norton. Okay, so we have our IN, we have our VTH, and what do we do? What do we need next? We need our equivalent RTH or RN, whatever, right? So for that, what do? We suppress the sources and draw the equivalent network. So this will become a short circuit. We have our, again we have our A and B here, right? We have our A, we have our B. This will be an open circuit. So this is 2 ohm, 1 ohm, 3 ohm. So we need to find R equivalent, let's say. So R equivalent is equal to this 3 and 1 will be in series. So 4 parallel 2, which is 4 into 2, 8 by 6, 4 by 3 ohm. Okay, so I think you are clear about this much. So we have what? We have VTH equal to, how much is VTH? 5 volt. We have IN is equal to 15 by 4 ampere, and we have RN is equal to RTH equal to 4 by 3 ohm. Okay, now let's draw Thevenin. Okay, 4 by 3 ohm, 5 volt, A, B, and the element that we removed was 2 ohm, right? So what will, and we have to find, our problem is not yet solved. We just found the equivalent circuit. Now we have to solve our final problem. So V is equal to what? 5 into 2 by 4 by 3 plus 2, right? A voltage division. which will come to 6 plus 4 10 by 2, it will come really 3 volt. Okay, now let's try Norton's equivalent of this was, right, what was the Norton's equivalent? And remember, always remember the thing that here we got we considered the I Norton or I short circuit as going from A to B, and we got a positive current, okay, positive value, that is the current is going from A to B. So here also when you're drawing, remember to draw the voltage source in such a way that the current goes from A to B. Okay, we have a 2 ohm resistance here, we have a 4 by 3 ohm here, and ITH is 15 by, sorry, IN is 15 by 4 ampere. So V equal to we have the current going through to will be 15 by 4 into 4 by 3 by 4 by 3 plus 2, that into 2, right? Total current division, current into resistance equal to voltage, right? So this will come to 15 by 4 into, this will be 4 by 10 into 2. So 4 and 4 will go here. We have 5 here. This will be again 3 volt. So our answer checks out. By using both Thevenin method and Thevenin equivalent circuit and Norton equivalent circuit, we get the same answer. So we can assume that our answer checks out. So I'll just go through it once more. We are not asked to find the Thevenin equivalent or anything. We are just asked to find the voltage. We are using the Thevenin or Norton equivalent. So first, to find the open circuit, first of all we define the terminals A and B, X and Y, whatever. We define the terminals across which we want to find the equivalent network, equivalent circuit. Okay, then we find the open circuit voltage, which will be the Thevenin voltage. We find the short circuit current, which will be the Norton current, and we find the equivalent resistance. See, this is the part where all the change comes, right? Equivalent resistance. Since this is a category 1 where only independent sources are there, we can directly suppress the sources and find the equivalent resistance across the terminal, and we got the value. Then using the values, we represent the Thevenin equivalent circuit and Norton equivalent circuit. From there we calculate the required value, and it checks out. Okay, with that we'll wind up this lecture, and in the next lecture we will check out the other category 2, and if time permits we'll go into category 3 also. Thank you.